So one of the topics that we always discuss when we discuss optical fibers is, of course, electromagnetic compatibility. And with that, we directly go to, oh, let's see, walking through the add-on material here. Is what my colleagues, Jamila and Michael from BMW, are going to present is, does cable shielding prevent all EMC challenges? So please go ahead.
Okay, thank you very much. I'm glad to be here, and also thank you for your attendance. Today we will be presenting the topic of shielded cables together with my colleague, and specifically we will be addressing the EMC challenges associated with it. To the agenda, we will begin with the background of the topic, why we see the necessity to address this, and then we will move forward in terms of the system implementation, comparing old versus new system aspects. We will then discuss, so to say, challenges associated with shielded cables. And also very important is to address some recommendations of how to prevent these interferences. And lastly, of course, the summary of this presentation. Yeah, it's interesting. I mean, shielded cables are being used already in different applications within the automotive industry, but it still raises the question why we need to discuss this today. The different legacy bus systems are deploying unshielded cable systems, but I think it was in one of the presentations addressed that as we go higher in terms of the data rates, we are expecting a lot of ME issues. And this, when you look at some signal aspects, like electrically associated properties of the signals, taking as an example the voltage amplitude, this is becomes really sensitive with increasing data rates. And that, of course, comes with topics like the crosstalk or other noise interferences, which could either be inductively or even capacitively coupled. The image here on this slide represents the power spectral density for 1000 base T1. What we can see there is that you have the SerDes, but also the multi-gigabit Ethernet covering a wide range of the frequency area. And what does this mean exactly? On the other side, we have the onboard radio communication systems, and we can see some overlap in some frequency areas. The impact of this is, of course, interferences between the systems. We already have currently implementations in terms of shielded cables that, so to say, cover this topic to some extent, and also consider the fact that we have around this system implementations very, very sensitive radio communication applications. But on the other side, shielded cables are also being widely used to those areas within the system which are, so to say, very sensitive in terms of the radio communication systems. We're going to go back a bit in terms of the basics of electrical engineering. I have experienced this myself very often, that even most of the hardware implementers, the expectations on what the shielded cables is supposed to do and what they want from it. The image on this slide describes the basic electrical aspects of a coaxial cable around it. Probably for some it's not really clear, but I will just give a brief description on that. Typically, you would have between the shield and the ground the so-called loop area, and you can present that with equivalent circuitry. So in electrical engineering terms, it will be either you're presenting that in form of electrical resistance, capacitor, inductance, or also conductance, which is an inverse of the resistor. On this image, what we can see is the so-called impedance. And it actually incorporates these different aspects I've just mentioned. So going back to my previous point, what do we expect from shielded cables? We can see that it's at the first level, it's the capacitively coupled interferences. And this is really basic physics. Why is that? Electric fields normally have to have a source and a terminating conducting material. By adding a shield, you're basically introducing an option where you could terminate these electric fields. And that's basically the first goal of using shielded cables, to tackle these electric field noise sources. Looking at other aspects in terms of common mode interferences, these are interferences that could either be from PHY transceivers. Shielded cables also address this to a large extent, I must say. What is also very interesting, and I always say this, in most cases, people also expect that magnetic field, either noise sources and emissions, may be tackled by shielded cables. But this is not always directly the case, and I really would like to emphasize not directly in the sense that when we consider shielded two-set pair cables, and you have, of course, a shielded cable and the pairs inside are twisted, automatically the magnetic flux that is created there would be, so to say, negated, because the current flowing along these two conductors is flowing in different directions, of course, with the same magnitude. But in most cases, people would have, so to say, at the background that the expectation that this is due to the shielded cable, but it's not. The other point we have to consider is when we have a single conductor, let's say in this case like a coaxial cable, these magnetic emissions can be tackled with a shielded cable, but only under one condition. The current flowing through the shielded line has to be the same, of the same magnitude, but of different direction. But when you're implementing this at the system level, it's almost impossible to be able to do this. So it can happen, I would even say it accidentally, but if it happens, then only then we can say that shielded cable, or specifically a shielded cable, has addressed these magnetic emissions. The other point I always like to say that it's a bonus, that through the usage of shielded cables that we attain more EMC margin, and that is due to the summation of unbalanced and screening attenuation. Lastly, as a key point, this is also another point I would like to say, yeah, so to say, shielded cables address magnetic noise sources indirectly. And here we see that you have, in this case, a shield to ground loop area. If you can contain this, and also if you can contain any interferences due to probably wrong implementations in the termination, then you can tackle these noise sources. But if that's not the case, then you cannot really say that you're using shielded cables to address this. Good, and now we would like to address some of the old versus new system implementation aspects with my colleague, Michael.
Hello, after the first introduction of Jamila on shielding cable, some topics, what's changed when we're looking for newer systems like Ethernet? And one is the DAB issue. In old buses like CAN and even to the 100 megabit Ethernet, this DAB topic was not an issue. The main problems were in the area of the AM band in the lower megahertz range. Nowadays, the new buses, as we've seen in the one of the first slide, have a wide PSD range, and they come to the area of the FM and the DAB band. And in the picture, we see a screenshot of a spectrum analyzer in a rural area. And the 100 megahertz area, we see the spectrum of the FM stations, and about 170, we see the first bouquets of some DAB stations. And we can recognize that the DAB stations are about 15 dB lower than the FM stations. This is quite good, because normally the DAB should have a better signal noise ratio than the FM of about 18 dB. But one takeaway, this better signal noise ratio is already at the transmit station. And this is causing some problems. And we see it on the next page. Here we see a setup made at Erlangen at Fraunhofer Institute. We made a test emission with a very low density. And on the left, we see the PSD spectrum, and we see that we have in the lower area, we have no CSC errors if a 1000 base T1 link is off. This changes. The spectrum at the input doesn't change visible, but we get a lot of CSC errors and the transmission drop. And we should have in mind that DAB was sold as a system which has almost no noise, and here we see a complete drop, and it takes quite a lot of received packets until the correct reception is resumed again. So this and similar results brought BMW to the decision to use shielded twisted pair cables in their cars. And what's also, our system designers have amplified the gain of the antennas for DAB to receive it, so the problem of the DAB topic came more visible than before. Another topic for the shielding was the topic of crosstalk at multiport connectors. In the past, we have had quite a space between, we see it on the left picture, with an ADA system, here coax, but it's similar to SDP or Ethernet lines. They were widely spaced, and with the need for having more function within an ECU, the need came to bring more density on the connectors. And multi-port connectors with very close spacing between the different ports were developed. On the right, we see a measurement for crosstalk in the low frequency area, up to 10 megahertz. Crosstalk has almost no impact. It starts to get an impact in the range of 10 to 100. It's about a 10 dB increase in the crosstalk in this area. And we get a bigger increase in the gigahertz range. So crosstalk also is a topic which forces the need of shields. It was also a topic where during the development of connectors for gigabit solutions, during the development, shielding elements were introduced into the connectors. Now one step back. Why we were successful with plain twisted pair. We have seen here before that plain twisted pair was the base foundation of telephone for decades. And simple twisted pair cable works in the way that it's very symmetrical. And with symmetrics, we see, as we've seen in Jamila's foil, that we generate the current in both wires, and currents generate a field, an electrical field and a magnetic field, which are in opposite direction. And with the twisting, you repeat it every turn that it's changed the phase. And in the end, from the outside, you see a zero field. This change when you have an asymmetric. This worked very fine for 100 base T1 and give us the flexibility to be independent from the topology and the usage. But having unsymmetrics, we generate EMC, and the others is that for 1000 base T1, we have seen that with the pure symmetric approach, we came to a limit. This is also a reason why we introduced an SDP cabling. Now, saying we needed shielded cables, and we understand some topics about why shielded cabling works. We see also some other challenges where shielding cabling causing some problems. One is the topic when we have a noise generated internal within an ECU. The figure on the top shows a setup where you have a shielded cable, twisted pair inside, and a noise generator inside an ECU. The noise might be also not be only on the signal line inside the shield, but the noise might also be coupled to the shield itself. There are many ways. On the left, 3 of them. The most important topic is the capacitive coupling, which is done by parasitics, and it might be that the noise source is directly coupled to the shield. So you have a noise coming to the shield without it really intended to be. And the parasitic capacities are there. And what's also more critical, the parasitic capacitors have the trend to get a better coupling with the increased frequency. Below, two other topics are the resistive and inductive coupling. These are more done by direct components, and what is also, it's the resistive coupling works directly with the frequency, whereas the inductive coupling has a behavior that it's indirect coupled via frequency. So if the frequency range, the coupling goes down. This is very obvious that you have, when you have components, that you have this coupling, but it might also be, as shown on the left, that you have an indirect coupling via the ground distribution itself. So all components within an ECU have a certain impedance to ground, also the noise source, and the coupling might be indirectly done via the ground to the ECU and also to the shield. We see it later, but the topic might be that it's really important to take away noise sources whenever it's possible. Another topic for a shield might be overseen, that shield is a wire like any other. In this setup shown on the left side, it's a simplified setup where you put a noise source directly on the shield and try to measure how is the noise transported along the shield to a destination which is not intended to ECUs, but an external component. And we have done it in the lab with some PCI coils and moved them around. We have a perfectly shield, grounding the shield to the, we have perfectly grounded the shield to at both ends and move the coils around the shield. And in the figure below, you see we have a certain coupling. The coupling is dependent from the distance to the ground points of the setup and the distance between the shield and the length. But it's remarkable that even having different points in the setup, we get a certain maximum, which is more related to the length of the cable, but it's in a certain frequency range, here in the 25 megahertz range. You have an increase for the low frequencies to the frequency of about 25 megahertz. Then you have a very stable plateau with a comparable high level of coupling. So this setup shows it's possible to transport noise on the shield itself from an area where it's coupled into the system to an area where it might be harming the other systems. This might be the case, for example, for cameras, where you place the camera beside the GPS antenna. So the shielding wire is a wire as any other wire and can transport noise. One takeaway is to place shields, also if they were perfect, away from noise sources. The topic we found in a setup very interesting, but it related more to the figures we've seen in the noise source, noise coupling on ground, is that the ground impedance might take a role. On the left picture, you see a setup made in an EMC chamber. Here an additional optical transceiver, perfect optical transceiver, was added. Without the optical transceiver, the system has had no issues. Adding the optical transceiver, we start to having issues. The root cause was found that the optical transceiver has brought into the system a certain resonance in the ground impedance. It's shown on the right, where you have a very, very flat dip in the resonance curve of the ground impedance. Together with the burst of the DC-DC converter, which have a sharp repetitive frequency range, it was amplified up to the megahertz range. The solution was to damp the ground impedance in a certain way. And we see it below, the dip went away. It's a very, very small dip. And the DC-DC converters still have this burst. Now it's broader, but they cannot be amplified up to the megahertz range. So in this case, one topic is also with the shield, check for the ground impedance of the shield connection itself. With this few examples, I hand over to Jamila to give you some introduction how to prevent such shield interferences.
Good. Thank you, Michael. So let's proceed, I would say, to the interesting part. So hardware designing is always, I would say, the most critical part of the system architecture, system design. And mostly, or in most cases, the shield interferences have to be tackled at a later time frame, where the development has really reached a matured state, where it's also very difficult to tackle these problems. Now, I think this is something that is very minimally practiced within the industry, that the system grounding concept has to be predefined in the initial design phase. And this is I would say it's a prerequisite, because only then you can think of all the aspects in terms of which communication interfaces are interconnected, what to consider as well. But also really going as low as what kind of signals have to be used within the different subsystems, in which frequency range do they operate, and of course, as low as voltage levels. Sorry. The image on the lower left of this slide describes the different ground potentials for different applications. And please do not confuse these different electrical potential. I would like to emphasize that do not mean that one has a higher magnitude than the other, but they just serve it for demonstration purpose. And what I would like to emphasize is when you really take a look at the lower left side of that image, you can see that there is a specific shield ground dedicated for that. And this is then electrically connected directly to a clamp, either 30 or 31 ground. And this is, so to say, the key takeaway of this slide, and I even took a bit of more time to emphasize on that. This is normally not the case in most of the system or hardware implementations currently. You would have the shield ground being shared within a printed circuit board with other applications in terms of, it could be either an analog ground, or in some cases you could also have a single ground within the printed circuit board. The image on the right just emphasizes on what I just explained, but at I call it a subsystem level printed circuit board. And you can see the gray dashed rectangle representing that, what I was just explaining, that this is a dedicated shield ground. I know there will be questions probably on this in terms of splitting the grounds, but the focus is shield. Of course, there are several aspects that have to be considered on how to implement the whole subsystem to ensure that also other EMC aspects are covered. But it's also, on the other side, relevant to have an understanding that when we're using a shield, then it should be effective. And of course, that includes how it's implemented. We can also see on this gray marked rectangle different connector systems, which is normally the case. And what we also see, it's very in a small image, some parallel connected capacitors which connect the shield to ground. But I'll get on this in the next slide. Of course, you would have other grounding schemes within a subsystem. It could be analog, and some could also be galvanically isolated, like what we can see here in the high load ground range. This is a very controversial topic as to whether or not to terminate the ends of the shielded cable. And emphasizing on what I said before, when we look at the shield effectiveness, terminating the shield line correctly, I would say is compulsory. It's not an option. And usually, of course, you would use alternating current coupling capacitors to serve this purpose. And you also have to, in the implementation, consider the fact that when you are connecting these capacitors, of course, you have to ensure a so-called low impedance path. which also has to be considered at the printed circuit board level, considering other parasitic aspects like inductances that may occur within the printed circuit board. This is very crucial. On the lower left of this slide, we have these two green images, which normally would present, once again, a printed circuit board. And on one side, I take this as let's consider it as a typical communication channel between an ECU and a camera sensor. On one side, you would have a single port connector, on the other side, a multi-port connector. And what we can see here is that on the left side, the one with the PCB with a single port, you have the parallel AC coupling capacitors I just mentioned. What we can also see that there should also be a possibility to connect that ground directly to a clamp 30 or 31. The two images on the right, looking at the upper one, we partly addressed this in the previous slides, but I would like to revisit this once again to emphasize once again on the ground loop area. And we can see there's two, so to say, not exactly circles, but ellipses. The upper one, the green marked one, and the lower one, which is red dashed one. So the upper one is, so to say, the area where we prefer to be. This is, please do not confuse, this is not quantified at the moment on this image, but it's of course mathematically possible to do this. And this, of course, contributes a lot to what extent the magnetic flux created within this area would either increase or decrease, because of course the magnetic flux has an influence on the induced current, which of course will contribute to noises on the shield line. The two lower images describe a typical harness cable bundling, so to say, where you would have typically different communication interfaces, analog, SerDes, Ethernet, etc. And what I would like to emphasize here is the fact that it's also important to see how to best define this configuration, which cables should be bundled with which ones, and that with the aim of reducing the dipole antenna that may be created with it. Why? Of course, because this obviously creates extra noise sources. Good. And to summarize it all, despite all the addressed, I would say, some negative topics in terms of the shielded cables and to what extent this impacts EMC issues, I would still emphasize that this is still essential to use, not only for the current communication systems with medium range data rates, but also for the upcoming even higher data rates. It comes with a but, that there is a prerequisite, there has to be a system ground concept predefined, which is normally not the case, and accompanied with this, there has to be a dedicated shield ground defined as well. Some takeaways, as mentioned before, or probably missed out on that, but the electrical ground planes are never going to be ideal. This cannot happen. But it can be, so to say, these variations in terms of impedance can be or have to be analyzed from system application to system application. Because for some system applications, such variations may not have a very large impact. Another point I would like to emphasize is to have an understanding what shielded cables are really meant to tackle in terms of noise sources. More on the capacitively coupled noise sources, and in some cases inductively coupled, but one has to really look on the implementation. The topic of the system ground is addressed before. That's also a key and a prerequisite. And the topic of termination is also an important topic as addressed, that as we go higher with frequency, it's also crucial to incorporate proper termination, because only then the effectiveness of using a shielded cables can be guaranteed. And lastly, Shielded cables, even though they would tackle some noise sources, but we have to remember that they only focus on transitioning these noise sources to other less sensitive areas. So if we really want to focus on tackling these noise sources from the beginning, not only to address the aspects that I've mentioned, but also to ensure that those noise sources are not existing at all. And this concludes our presentation for today, and I'm very curious of the discussion round. Thank you.
Okay, thank you, Jamila and Michael. We have time for one question, and I see Haysam getting ready. Okay, well, we have later a break, but please go ahead.
Okay, so the first question, which I'll make it only the first question, is on 1000 base T1, it was targeted for JUTP. And I see that in one of the slides you said that you're transitioning to STP. Is this only in the case where you're routing close to an antenna because of the pickup, or is this for all applications for 1000?
Currently, it's for all applications. It's currently for all applications.
Okay, and then why is the concern from if the transceiver is designed with an alien crosstalk from the IEEE spec to handle unshielded, what's the concern by going to shielding in this case?
So if you want to have an effective crosstalk elimination, you need a distance of about more than 6 millimeters. And in the case of the connectors, you came down to below 3 millimeters distances. So that was not possible. Step by step, all connector manufacturers introduced some shielding between each ports. And this was also the good starting point for introducing the shield, because then we just have to contact this shield with the cable. Then we have had an STP solution. That's the reason why we have now two classes in the TC9, the class 1, which reflect the transition from the unshielded twisted pair to the STP. That's class 1. And the class 2 is the one with a really full 360-degree shield and basic on the shielding effectiveness.
Last question here, last comment. Is this due to the unrealistic crosstalk limits in IEEE?
Cannot say that's unrealistic, but they had set a quite high limit to fulfill the requirements. But the main reason was not the crosstalk. The main reason was really the change over from the DAB reception. We have about 2 antennas in the car. We have a DVB-T. We have 3 antennas, so you cannot stay away from the antennas anymore. And the antennas look outside for the reception, and they look inside for our cables. That's a fact.
So the argument would be that's relative based on the car routing, essentially, right?
No, the argument is that the DAB is more sensitive than defined for.
Okay.
So there are more reasons for this, but one was really that we have a very robust 1000 base T1 system, which has some spare room for reduction, and we have a very sensitive DAB system. So this was contradicting.
Mm-hmm.
Thank you.
We have one question online, I think.
All right, we have an online question from Harry Parmar. When designing your hardware grounding system terminations, how do you take account of potential grounding variability along the length of the vehicle, and also how this may vary with time from new vehicles to older vehicles, say over 10 years?
I would say in most cases you anyhow have most of the different hardware subsystems designed between different tier 1s. So I still see that as a responsibility of the OEM to ensure that these different interfaces are brought together to define a single system. Does that answer the question?
It's always
Yeah,
difficult to say with the online participants. That's a bit unfortunate, I suppose.
So there has to be a single system ground configuration. And if we consider the fact that you have probably different implementers, still there has to be an understanding how the system grounding scheme should be at the first level. So when the others, the remaining implementers are implementing this different subsystem or whatever you would like to call it, the grounding system of it, one is already aware what the end complete system grounding scheme is supposed to be. I hope so. I hope it answers the question.
Okay, thank you once more, Jamila and Michael, for the presentation.